This is the in-progress presentation for our senior design team. Our project is VR learning environment with real-time brain signal monitoring, and I'm Zane Fravit.
I'm Yumna Rizvi.
I'm Ethan Lee.
I'm Brendan Jenkins.
And I'm Jacob Mitchell. Now for a short introduction of our project. Our project is a virtual reality learning environment that provides real-time monitoring of the user's physiological state using brain signals obtained from the Epoch Plus. The user interacts with the virtual reality modules using a Leap Motion controller. These modules are designed to help students learn in a classroom environment, and they highlight important learning lessons. Our project will provide the educator an insight into the student's understanding of a lesson, allowing them to see real-time brain signals and understanding of a student as they go through the module, whether they're bored, whether they're stressed, whether they're enjoying it, things like that. And this helps so that students that need extra help are able to get it from the teacher. Additionally, the teacher can connect directly to the student's module, allowing them to view the student as he's working and, again, have the physiological data. Now for the system overview. This is our level 1 diagram. You can see right here that we have external distractions and the user being fed into the Epoch Plus. This is where it monitors brain signal data. The motion data right here is going to be gathered from the Epoch Plus as well. This is for looking around in the virtual environment. This Epoch Plus data is also going to be fed, and this is the EEG data. This will be fed in the performance metrics in the Unity game engine. This allows for us to actually see the stress levels, things like that. The user will also be inputting motion for their hands in the VR environment using the Leap Motion. This is also going to be fed into the Unity game engine. This Unity game engine will then be able to output a student view and a teacher hub, allowing for the student to interact with the environment as well as the teacher to monitor their physiological and actually tune in to see what they're doing. Our level 2 system architecture includes the student data going in through specifically just the Leap Motion to control the VR hands, and the Epoch Plus, which is going to feed into the Emotive Cortex API, which allows us to get the motion and EEG data for physiological and looking around in the environment. Our Unity game engine is going to get the information from the Leap Motion and the information from the EEG in the motion for looking around. It's going to go into the Unity game engine, it's going to be interpreted, and then it's going to be exported as the teacher view and the student view. We've covered what those will be. The next part of our level 2 architecture is the teacher view feeding into, or the teacher view scene and the student view scenes feeding into their respective boxes. This is going to show that this is going to allow the student to see their virtual environment and allow the teacher to monitor them. This is going to feed to the teacher's monitor screen for their computer and the student's VR headset so that they are both able to see these.
So this is the logistics of our project so far. The task progression. So we have our interactive classroom environment pretty much almost done. So the only thing that we have left is our classroom modules. We still have to finish processing some variables to finish up the module. The controller testing is pretty much done. Implementing the controller into our environment is pretty much done. The last couple of things we have to do with our VR headset is just 3D printing a couple of additional pieces onto our headset, as well as um, getting some physical parts such as the band to go around your head and stuff like that to be able to fit with our emotive. Some more stuff that we have for our task progression. We finished communication of EEG data to our software. We have the brain signal data. That's almost done. We just need to finish processing the performance metrics into our game. And then lastly, we have the integration of hardware and software. We pretty much are in that phase right now. We still have to debug some things in our program. And apart from that, we still have to completely finish building our VR headset to interact with our classroom environment as well. So now for our summary of achievements versus our schedule. So we have an interactive classroom environment developed. We pretty much reached that target apart from passing a couple of variables, the date of February the 12th. System hardware integration, we pretty much have that completely finished. The systems integration for software, we are on target for that. We just have to debug a couple of things within our program. And that kind of leads into that next task, the overall system integration debug phase of when we're debugging everything put together. That's still in progress because we're currently doing that right now. So one of the first things that we were able to do was get the emotive data in Unity from the Cortex app. So we did this in Unity by creating a Cortex app, like I mentioned, which enabled us to develop a third-party application in Unity that interacts with the emotive headset. The Cortex API is built on JSON and WebSockets, making it easier to access from a variety of programming languages and platforms. So obviously, the platform we used was Unity, and our programming language that we're using within Unity is C#. So in the figure, it shows us reading EEG data consisting from 14 nodes from the headset, motion data from a 9-axis inertial measurement unit consisting of quaternion data, a 3-axis gyroscope, a 3-axis accelerometer, and a magnetometer. And lastly, the performance metrics data shown at the bottom, which outputs different emotional statistics. As a side note, the code documentation for how the data stream works is linked below on the slide. And here's a video of the data working in Unity. And we first start by running our program in Unity. And it then lets us be able to connect to the Unity program through Bluetooth. And this is the stage where you would have to make sure you have good contact quality, and that will update as you go. And this is us subscribing to the different streams of data, which includes the EEG data, the motion data, and the performance metrics. In this video, it didn't not include the performance metrics because it takes a while for the performance metrics to show up. So that's why it kind of took a while for this video. But yeah, that's pretty much it for the performance metrics within Unity.
So the thing that we are currently experimenting with and hope to finish have it being done by 4/1, which is our software implementation deadline, is the teacher hub. Right now we have a working local teacher hub, which means that we can host this on a local network. So if there is somebody on the same router as you, but on a different computer, the teacher can host it, the student can connect, and they can read values from stress, engagement, focused, interest, relaxation, and excitement. These are coming from the performance metrics through the emotive. So our next step in this is we're going to get it over a server so that the teacher can host from anywhere and the students can join from anywhere. They don't have to be in the same local network. This is important because if we're trying to do this for virtual learning, not everybody's going to be on the same local system. So here I have a short video demonstrating how it works. You can see that for the teacher, you are able to click the host button, and on the students, you're able to join. For the future, you will be able to enter the IP address of the server in order to join the teacher. The teacher can start hosting, and they immediately get this screen. You can see that they're not getting any values yet because none of the students have joined. As soon as the student joins, you can see the values start to pop up, and they'll be able to read. We're going to have some simple bounds that make that easier to read for the teacher so that they can actually understand it easier. You can see that the student can also look around. This is the second student joins. You can see that more values start to pop up. These are for the second student. You can also see that the student can move and look around using a basic student model. The modules that we have implemented currently, you won't be able to move around, but you can look around. So this would be something that we could implement for the future. If we wanted to implement a full classroom, we could have all of the students sitting in a classroom, able to look around, able to look at each other, able to move through the classroom.
We're looking at using the motion data from the emotive headset for head tracking through our Unity environment. We were exploring a couple different methods of head tracking. One of the possible things that we were thinking of using was a phone as a screen instead of the LCD, but we figured that if we used the emotive, we could save on costs, and it was a little bit difficult to implement the phone because we didn't really have a way to test it. The emotive headset does contain many values for its motion data. It contains accelerometer data, gyroscope data, and quaternion values. The values from the motion data are sent to a Unity script, and this Unity script decodes the data into things that can actually be used in Unity. We were thinking about using the accelerometer and gyroscope data at first, but we realized that quaternion data actually takes those two into account. So the plan for reading the the information from the gyros or from the quaternion values is to take the data stream that we have in Unity and obtain the values from the channels. And then those values will be mapped into Euler angles. And the reason that we are doing this is because the values that the quaternions have on the emotive are mapped differently in the real world as they would be in the Unity environment. So we take the real values and map them to Euler angles in Unity, and then turn these into quaternion game objects to be displayed for camera rotation. This video demonstrates how we're going to use the quaternion data for head rotation. So after subscribing to the emotive headset, we don't have it connected on the head for the demonstration of this video, but as you can see, you have the motion data. So the last four numbers here are the quaternion values, the three before that are the gyroscope, and the three before that are the accelerometer values. Upon the game's start, we actually haven't figured out how to center it onto what we want it to be centered onto. But as you can see, the environment doesn't float with the movement of the headset, or when the headset's sitting still, it doesn't float the environment because we've bounded it. It actually moves in each direction with the headset movement. When we were looking at implementing our game module, we decided the first thing that we should do should be a module aimed towards younger students, because the actual lesson behind this would be a little bit simpler to implement in Unity. And we decided to do this because of lack of Unity experience. We did not have experience with implementing SDKs or any C# experience in the group. So this was a good way to learn how to do all of this stuff. And after creating this module, we do have all the skills necessary to implement additional modules in the future. There are several things that this module implements. First, we have random scene generation. So in order for it to be a game that people can actually learn from, we can't have repeated scenes. So we randomized two things in this game. The first thing we randomized was the number of fruits. We've created an environment that has different fruits on different tables. So a randomized number of fruits will be created to keep the counting different and teach about numbers. While the second thing that's randomized is the type of fruit that spawned, which can also teach names of different types of fruits to students. This also required multiple despawning scripts to keep the game running smoothly. The range of the Leap Motion camera in the Unity environment is very small. So if you do not have proper spacing, the fruits can get out of range very easily. So we implemented a way that if the fruits get out of the user's range and touch the floor, then the fruits will respawn back to where they started at. But upon putting the fruit in the basket where the incremental counter is, it'll despawn the fruit from the game. And the game will continue, or the module will continue, until the fruits are all placed into the basket, and then it will continue to the next level. We haven't yet decided a total number of completions of this scene for a completion of the module, but we are currently working on stitching all of these pieces together. This video shows the functionality of our Unity module. As you can see, there is a scene view and a game view. And in order to demonstrate the functionality of this module, we need to use both of these views since the head tracking is not currently implemented properly. This is just the basic setup for our 3D environment. You can see two tables, and then there's also walls behind where the fruits will spawn in, so they can't roll out of the player's range. And then there's also a basket in the background that is what triggers the counting. The fruits spawn in semicircles on the tables, and they also spawn in random numbers. So you can see on a repeat of the game in 1 second that the types of fruit and the number of fruit that spawn per table are going to be different every time the game loads in. When a fruit is moved from a location to inside the box, you can see in the game view on the right side that as the fruit comes in contact with the bottom of the box, it actually will despawn the fruit. Right here. And then if you look at the value, which we do not have printing to the screen as of now, but in the bottom right, there's a counter value, and that counter will increment every time a fruit comes in contact with the box. This is a video demonstration of our first person view. As you can see, this is about 45 degrees, so this would be in between where the player can actually look to. As you can see, when the fruits touch the floor, they spawn back onto the table, and when the fruits are placed into the box, they despawn from the game. This would be able to help students if they couldn't get the fruits into the right place, because Unity is a little bit buggy. It'll put it on the table and allow them to try again.
In mid-January, we made our first attempt at integrating all the systems. Previously to this, we had all systems capable of running individually. We were able to get success in some parts throughout the system, however, we also encountered a few problems that stopped us from moving forward. From a hardware point of view, the USB-C hub allowed us to mitigate excess wiring tangling in between the systems. This hub was placed on top of the headset. An issue we found with the NeoTab is that our screen plus the HDMI cord is ever so slightly bigger than the compartment allowed. At the time of our early experimentation, we did not have the 3D printed headset completed, so we continued experimenting with the NeoTab. We want the custom headset to be our primary headset. However, through testing, we have noticed that precise measurements not achieved through 3D printing is causing the VR effect to not be as immersive. From the software point of view, our core module is done, and all other modules build off of it. We use C# scripts for creating the module behaviors. These behaviors included spawning of objects, true randomization of the starting scene, which was used to create a more lively interaction with the user, and the restoration of out-of-range or dropped objects. Currently, for the module layout, it is strictly made for functionality due to ongoing testing and integration. We plan to integrate classroom aesthetics soon, as we have the assets for it already. With the emotive integration, we have all of the information sent by the Cortex API accessible to our module. At the moment, we are configuring the motion data within Unity to be calibrated for head tracking. For the Leap Motion, we have incorporated the Leap Motion SDK within Unity. This provided us smooth integration of controller data within the scenes. The controller allows us to navigate through a menu to move within the scenes. With our module, we encountered a critical hurdle in our design. We originally planned to use Google Cardboard View to display the module through a phone, but the package was inefficient. Our workaround was to use the Unity XR plugin, splitting the screen into two halves and presenting it on a portable screen. With the Teacher Hub, we have the full design working through a connection made locally. This means that the two instances must be on the same network to view it. However, this is inadvisable for us as we want this to be a distance learning aid module. A locally owned server is currently being set up and tested to allow for both modules to connect onto. The menu in these scenes allow for users to join or host their module, giving freedom to the user if they prefer private servers.
For problems and surprises we have encountered in the progress of our project or collaboration efforts, we didn't anticipate it to be as difficult as it was to collaborate due to the nature of the Emotive Pro subscription. We found it hard as a team to collaborate with our hardware and software in a time-efficient manner with our while avoiding one person with the majority of the load, since hardware and software needed to be integrated together. The reason for this was mainly because of social distancing requirements because of the COVID virus. Another surprise we encountered was the integration of components in Unity. The members of our group had to learn the skills and tools required for this project, such as C#. This made scripting a bit more of a lengthy process because of the trial and error and research process included. We encountered unexpected bugs and glitches along the way. We also found that SDK packages for Leap Motion and Emotive required a long time just to shift through files and even longer to integrate them into our project. Also, reading raw data from the Emotive requires reading information for the Cortex API, which uses JavaScript, which no one had experience formatting and required more time. We have experienced unexpected sizing issues with our 3D printed headset. We realized using the LCD screen with the USB-C hub causes display problems. Our project also included a modeled VR headset, which requires precise placement to give full VR effect. We also need to modify the NeoTab to fit the LCD. Next, I'll talk about our action plan going forward. For what we plan on doing going forward, our action plan consists of continuing software development to create more modules to explore the full dimensions of our project. We will continue debugging and fixing any system integration issues, as well as optimizing our system integration. We will also finish buying small components needed for the construction of our hardware for comfort and optics of our hardware and prepare for our final document. We will also implement any constructive criticism into our project that we receive from the faculty, and we will finalize the physical headset construction. Next, I will talk about the testing process for our project. For tests that need to be conducted, the first one is to incorporate a teacher hub on a server to import user data from anywhere. This consists of a host server, 2 instances of the Unity to show the teacher hub and student scenes connected over a server. This would mean the teacher would have real-time information from the student's activity in the teacher hub. For our third test, we will oversee proper calibration of head tracking in our environment by tweaking our C# script for accuracy of movement. Currently, we have our script that links motion data from the emotive headset to the Unity environment, moving the main camera at the same time as the headset. Although right now we are moving the camera, the axes are not properly mapped to the emotive movement. The plan for this test is to use some of Unity's statics methods for manipulating quaternion data in order to fix the accuracy of head tracking. We will test out different combinations of vector 3 constraints to determine which one properly maps emotive data to the Unity axis. The criteria for passing and completion of this test will be for the user to be able to rotate their head 360 degrees around them, mapping to the Unity camera with no accuracy and without bugs.
For our third test, we plan to compare the performance metrics generated by the Epoch Plus to the actual metrics felt by the user. We will do this by subscribing to the metric data sent by the Epoch, noting down the user's metrics by asking them specific questions directly related to the metrics. Lastly, we will compare the metrics to each other. To move on from this test, the difference between the metrics must be no more than 10%, allowing for minimal technical errors. For the last test, we will be testing the stability of the system compatibility once all equipment is strapped onto the user. The reason for this is because the sensor placement has previously had issues when ever so slightly moved, so this is to ensure that the signals are still correct. The plan to test the stability is to slowly add on multiple components while sending brain signals to the modules. After adding all the components, compare and make sure the brain signals and connection points are correct. For completion of the test, the readings must be similar to each other from the ladder of integrating the systems. Questions or discussions?